Now we're going to do capacitors in, in series. Okay, so in series, I just described to you in the last video what that means. It means they're all kind of in a line. So there are no alternate paths for current to go by. There's just one path, so that's called series. So these capacitors are in series. This is once again C1, C2, C3. This time, however, we only know the voltage here is equal to V and the voltage here is equal to 0. But remember from our very basic definition of electric potential, the path to get from A to B doesn't matter. So if the voltage difference from here to here is V total, then the voltage difference from here to here must also be equal to V, right? Well, what is the voltage difference here? Well, once again, C1, and this time we don't know that this V, and this V are the same. So we have C1, V1, C2, V2, C3, V3. That's what we know about each of these. Now, let's look at what we have right here, however. Right here, before we hook this circuit up, what is the charge on this right here? Charge is 0. Its net charge is 0. So we know this is neutral. So that means whatever plus Q we have over here, it's going to come up with a minus Q right here, but that's going to put an exactly equal plus Q right there. And the same thing here, this will be a minus Q, this will be a plus Q, and this will be a minus Q. So what we know is that these charges are equal. So what we know then is that C1, so what do we, okay. C1, V1 equals Q. So once again, I got myself kind of going in a path that got there, but it was taking too long, so I just see it something like there. So I stopped and restarted. Okay, so C1 V1 equals Q, but so does C2 V2, and this equals C3 V3. Okay, so that's one thing we know. Next thing we know is how much charge is actually being stored here. Well, really, what do we have? This balances out, so this is 0. This is 0. So really what we have is we have some equivalent capacitor here, whatever it is. We have this that's really just this one and this one. And that means we really are just storing a charge of Q. So our equivalent capacitance is just going to be equal to whatever that Q is divided by our total voltage. And this will be equal to C equivalent. Okay, so this is what we are looking for. Once again, we're trying to replace this series of 3 capacitors with 1 capacitor. And this is what we're going to use to get there. So what other thing do we know? Well, we know once again from the very basics, we know that the potential difference between here and here must total V. And we also know the potential difference between here and here is just V1 plus V2 plus V3. And we know that equals V. Well, what is V1, V2, and V3? That's just using this definition right here, we can substitute in for each of those. V1 is just Q over C1. V2 is Q over C2. And V3 is Q over C3. So, what does this give us? This gives us Q, times 1 over C1 plus 1 over C2 plus 1 over C3 equals our record. I screwed myself up twice in the middle of things, so starting again. So what is this equal to? This is equal to V, right? Well, what's our total V equal to? By this definition right here, we see that this is equal to, it is equal to Q, which is our Q total, but Q divided by C equivalent is what this, just by definition, right? That's what V, our V total is. Well, do we just divide both of these by here, and we see that 1 over C equivalent equals 1 over C1 plus 1 over C2 plus 1 over C3 plus however many you have. All right, so that is how capacitors add in series. If you have capacitors in series, the equivalent capacitance, 1 over the equivalent capacitance, is equal to this. We'll sometimes write that, matter of fact, we'll frequently write that as the C equivalent equals this, oops, that can be on there now. This to the minus 1. In other words, the inverse of the sum. So you sum up, you invert each capacitance, and then you add those together, and then you invert the sum that you end up with. Okay, that's that. We have, the only thing we have left to deal with in Chapter 24 is dielectrics.